Okay, so let's proceed with another displacement-based solution. So you are actually at this point at a stage where you could easily, for instance, solve this problem on your own. But let me solve it again myself so that I can highlight a few points. But you'll see that many of the features of the solution is now, they are individually shared by other problems we considered before. So for instance, a part of the solution, I'm going to talk about the pressurized thin-walled cylinder. Naturally, it's going to look a little bit like the sphere case. But at some point, we will obtain a differential equation that we have solved for the cylinder torsion case, for instance. Okay, so bits and pieces have been sort of considered before, but by itself, it constitutes a new example. So let me solve it. And then we can also discuss a few new aspects of it as well. So pressurized thick-walled cylinder. Eventually, this is going to be, or I would like to highlight the plane strain aspect of this problem. I will remind you what that means, or we will recall together. And next time when we meet, we're going to solve a plane stress problem. Okay. The problem is that we have now a cylinder. Let's draw this again. That is supported or attached to two supports, walls at the end. Okay. It has a certain wall thickness. Okay. And this is the axis of the cylinder. The axial position really does not matter so much for us in this problem, but I'm going to take the z equals 0 point to be the center of the cylinder, and this would be our radial position. And then the total length of the cylinder is L, so we have L over 2, L over 2. And the inner radius, eventually, it's A, and the outer radius is going to be B. And if I also take, as an alternative view, a cross-section of the cylinder at, let's say, z equals 0, then what I will see is, okay, that's the cross-section. And there is now an internal pressure, PA. And let's assume that there is, for generality, also an outer pressure. Outer pressure is PB. Okay. A few other conditions, by now we are familiar with them. So at these supports, usually we have, and in this case as well, U is equal to 0. So the displacement is completely constrained. And at the right-hand side as well, U is equal to 0. We have no body force. We have no acceleration. And in addition to these displacement boundary conditions, the pressure acts as also a boundary condition, just as in the spherical pressure vessel problem, or the pressurized thick-walled sphere problem. We have, in this case, the radial stress is equal to minus PA at R equals A, and it's equal to minus PB at R equals B. Okay, that is the problem setup. So things were a little bit neater in the spherical case. In the spherical case, in fact, it's one of the neatest problems you could possibly hope for. There's almost no approximation, perfect symmetry and everything. So there, we have the sphere, and it expands, and we have radial displacement. Everything is obvious. So in this case, there's a little complication that arises eventually from the end conditions. So there is an internal pressure, which is going to try to increase the radius, right? But the ends are fixed. So these points cannot really move. So if you look at the displacement field at the beginning, it's not so easy to immediately interpret what is going on. So let's start with the displacement field. So we have U. In general, it has a UR, a U theta, and a UZ. And it's always good to put in all the possible dependents in those components. So, now obviously we have rotational symmetry, so I'm sure that eventually, or quite confident, let's say, that there is no dependence on theta for any one of these components. In fact, for the angular displacement, we can immediately say that it does not exist at all. So it's not there to begin with. Now, there is going to be a radial displacement. But the radial displacement at this point is fixed. At this point, it's not. So obviously, as I move along the axis of the cylinder for this original setup, I cannot immediately eliminate this z dependence. So this is a bit of a problem for me presently. Likewise, well, eventually this thing is going to deform in a strange way. So it's fixed there, and then it will blow up to a larger radius, come back down to the fixed support. There is no reason why I should omit UZ from the outset either. And now if I want to solve the problem in this setting where there is no U theta, well, whether it depends on theta or not doesn't matter. U theta is 0. I have UR, perhaps UZ, and both of them depend on R and Z. And we've seen a situation like this before where I had a cylinder and I was pulling on it. And obviously, the complication is arising from the end effects. So let's have a look at what those end effects are and if we could possibly simplify something. So the reality of the deformation, let's say, is the following. And I will exaggerate the situation with sort of a short cylinder. Okay, and I'm taking a cut along the, I'm taking a cut along the axis of the cylinder, and that's what I see. That's the cross section. Okay, and that's the initial view for the cylinder. And so what I have just discussed is that these ends are fixed, but it's trying to blow up the cylinder like a balloon. And there's going to be some sort of a displacement like this, right? And likewise at these ends as well. And that is the complication. Now, I can try to sort of, in order to make a more point, idealize this a tiny bit. And we're going to observe this in a numerical example. I think we will have time. So what you will see is there is a rapid increase in the radial displacement, and then it sort of saturates. But if the cylinder is very thin, this region over which you observe a saturation is very short. But nevertheless, as soon as it is not, if it's not extremely short, if it's of a certain length, then you will see that there is eventually, we will observe this together, a certain length scale at both ends because of the symmetry, over which these end effects dominate, and then the radial position sort of saturates, right? And moreover, what we will observe is that, okay, so these are our arguments. What we will observe is that if we take even a longer cylinder, so let me take this new example, a longer one. Again, I'm showing the cut across the axis of the cylinder. What we will observe is that these and the region over which we have these end effects, so length of L, sort of depends on the problem setup. The problem setup involves the geometry, the material properties, and perhaps, depending on the problem, the load conditions. But there's a certain length scale over which those end effects take place. In other words, if I draw this deformed configuration. Okay. This length is also approximately equal to L. Perhaps it's not perfectly equivalent, but what I'm trying to say is that as you make the cylinder longer and longer, right, there's a certain region over which these end effects occur. And over a very long range across the axis, it's as though there are no end effects. You see a very nice deformation that is in the purely radial direction. In other words, the z dependence of the radial displacement, it seems, can be omitted. Okay, and then you come towards the other hand, and it's the same thing. And there's a length scale. So if you make it even longer and longer, you will see that these end effects are always pretty much fixed to a region with length small l. So this L is just like we discussed before for the tension problem, representative length scale for end effects. And it has to do with geometry, material properties, and a loading. So if you torque or pull, those end effects might be of different absolute value, but eventually for a given setup of the problem, the end effect is of a certain dimension. And so the idea is that you start with a certain length of the cylinder L1, and L1 here, or L here, is of the order of L1, and L1 is this length. And now we have a longer cylinder, it's L2, and in this case, L is much, much less than L2, okay? So which means that if the length of the cylinder, in this case we called it L, if the length of the cylinder is sufficiently large, then I can idealize this problem. And perhaps just to highlight, we can idealize that setup with a situation where we imagine that there are two supports. And just for conceptual sort of, as a conceptual memory mark, I had called such supports frictionless magnet supports. So in other words, the surfaces of the cylinder can easily slide on these surfaces and not be constrained like this. They can easily move under the action of the pressure, but the supports can support tension. So if you pull, it pulls back like a magnet, right? So what we're going to do is we're going to idealize that scenario. So by essentially omitting what happens over here and concentrating on what happens only in the middle, so that after deformation, what we are going to see is essentially that. Okay? There's displacement in the radial direction and nothing else. So nothing else part is a little bit tricky. So in this deformation, there's obviously radial displacement in every case. There could possibly be a displacement in the z direction. So that is something that is not very easy to convince you. I'm going to show you the example. But essentially, because of this strange deformation, the displacement in the z direction, uz, in this case, is not necessarily zero. So for instance, in this region, this is sort of rotating. There is perhaps some displacement in the z direction. This portion is actually somewhat subjected to bending. You will see in the numerical example. Now, due to symmetry, of course, right across the middle, right there, because of the symmetry of the problem, this point cannot move left or right. So for sure here, uz is equal to 0. But here or there, it's not going to be 0. We'll see. As you make it longer, what we will observe is that, yes, here uz, due to symmetry, is for sure 0, but away from the end regions, in other words, in this region, we will see that uz is also almost equal to 0. Okay? This is just an observation. So in other words, in this idealized scenario, not only does the radial displacement depend only on the radial position and not on the axial position, the axial displacement will also be omitted. Okay? So omitting end effects means omitting those two terms. So these go because of the fact that we are omitting end effects. And remember, whenever we do this, in some sense, we are dealing one way or the other with the Saint-Venant's principle. Okay. Ultimately, it is linked to that concept. Okay. So now, before I go ahead and solve the problem, because this is now the displacement field, and in essence, I have simplified it to the point where the displacement field, let me squeeze it in here, it has only a radial component, and that radial component depends only on the radial position in cylindrical coordinates. So this is now the type of displacement that we would like to solve for. So I'll calculate the strain, calculate the stress, invoke equilibrium, and thereby close the loop to find the general form of U. And then we're going to invoke the boundary conditions, which are these, to find the constants that appear in that solution. Okay? So before I do that now, let me go ahead and show you a numerical example that demonstrates these points I was talking about. And that's the solution. We've already solved for it, right? So I'm showing only half of it, and 1/4 of it is chopped off. So what you're looking at here is for a given pressure, you're seeing the angular stress, the tangential stress that we solved for. And we know that that tangential stress varies for the thick-walled case. It's not a constant. It varies, and it varies considerably. So here, perhaps only relative magnitudes are important. So on the inside, I've drawn a picture of it, right? So along the radial position, the stress somehow has a decreasing tendency, both for the radial and the tangential components. And the tangential component starts off higher here of the order of 7 something. It doesn't really matter. It's relative to 2. So there is a change of more than 3 times when I move from the inside to the outside. There is a considerable change. Now, moreover, remember from last time, if it is thick-walled, the tangential stresses are of the order of the pressure. So for instance, if the inner radius is 1, outer radius is 2, the pressure is about 1 to 2 times, the tangential stress, is about 1 to 2 times the pressure, something like this. So the tangential stresses are of comparable magnitude to the radial stresses, so you cannot omit either one. And here the deformations are magnified, so actually deformations are small, but now you will see here the displacements. And of course, displacement on the inside is a bit larger, on the outside is smaller. All of these are things that we have actually solved for. Okay? But now what I'm going to do is I'm going to make the thickness smaller. So inner radius presently was 1. Okay? Outer radius was 2. I'm going to make the inner radius 1.9. Now 1.9, wall thickness becomes 0.1 over outer radius 2. 1 over 20 is the ratio. It's not quite thin-walled. Okay? But what we're going to essentially see is that the stresses, right, is changing by a factor of almost 3. The stresses are going to become much higher, and the variation is going to be much less. That's what we're looking for, because that is the nature of a thin-walled solution. So I go ahead and compute the new solution. Now, of course, because it's becoming thinner, the compliance of the thing as a whole, it's increasing. So it blows up like a balloon because the pressure is the same pressure, right? So it moved up so much, but remember, displacements are magnified. The point here is now, if you look at the stresses on the right, let me zoom in. This is the wall thickness, right? Previously, it was 7 times 10 to the minus 3. Now it's more than 10 times larger. And also, the variation is 9.05 to 9.5. So it's becoming less. So what that means is that now, with respect to the radial stresses, the pressure is at least 10 to 20 times larger. And also so radial stresses sort of can be omitted. And the tangential stresses are almost a constant. So the thinner it becomes, the better the thin wall approximation becomes. But if it is thick walled, there's nothing you can do. We are stuck with our more complicated solution with respect to this thin wall limit, which we covered in 232. Okay? So I just wanted to highlight that point. Now, I will go back to our present discussion, and I will open a model for the cylinder. So in this case, right, that's the cylinder. So I will show you two types of plots. In the 2D plots, you will observe, so that's a cut. I'm just, because of symmetry, right, it has rotational symmetry. You will see the tangential stress, and the displacements are always magnified. In the 3D case, you are seeing the axial displacement, right? Okay, so what I said is, first of all, right, you see these ends are fixed, and it blows up, right, in the middle, but it cannot move at the end, so that's the end effect. And due to the end effect, first of all, we see that there are significant changes in UZ across the radius, across the length. So UZ is obviously not omitted in this case. If you want to solve this setup, which you can solve numerically, but not at least with that analytical approach, with that simplification. And also, if you look at the tangential stress, eventually the tangential stress that we obtain will be a function of radial position only, because our solution is a function of radial position only. But here you see that the tangential stress varies along the axis as well. So also that is a effect of the end, right? So just because I can show a movie, I will show the movie as well, right? So we apply the pressure from the inside, and right, you have that expansion. So now we want to simplify that problem. And our argument is that if I make it longer, perhaps the solution qualitatively simplifies. So I will go ahead and change the parameters of the problem. So the length was 2. I will change the length to, let's say, 5. Now, the length is 2 originally. You will see that the end effects will be limited to about a length of 1. For this problem setup, the radius is, outer radius is 1, inner radius 0.6. So 1 seems large, but comparatively, it is of the order of the geometry parameters. So now I made it 5, the length, and I'm going to solve the problem once again. Okay? So now this is the stress, the cut. And now what you're seeing is already 5, right? 4 to 5. Over a distance of about 1 again. Now what happens, apparently our length scale is, representative length scale is about 1 in this setup. The radial stress, if I close these portions, is varying almost radially, as my solution, the simplified solution, will predict. So it seems that my arguments are holding, right? So the longer I make, I will plot perhaps one more, the better this approximation will become, right? So if we look at the displacements as well, what you will see is that, yes, at the ends there is some displacement, right? Axial displacement, but in the middle, so yellowish is 0. In the middle, in this region, it is close to yellow. Okay, so let me just, for the sake of argument, make only one more calculation, because it doesn't take so much time. Let's make it 20, okay? So now representative length scale was 1, 20 is, so half the length is 10, so it's 10 times larger, the cylinder length. Okay, so now this is the axial view. Now if I zoom in, if I want to see a significant portion, I have to zoom in. And that's the variation of the radial stress. So obviously, nothing is happening. I can move up, right? Or down the cylinder. All you see is a radial variation. So all across that region, my solution will be perfect until eventually I come to the end. But that's what we're omitting, essentially. And likewise, if you look at the displacement, right, it's in that region. So it's 0. So my approximation seemed to work quite well. Okay? So That is the numerics. And now we're going to solve that problem because it's so much simpler analytically, right? So while I'm closing this thing off, let me also highlight, one thing that perhaps I mentioned in the introduction. We are doing analytical reasons. These things are not quite outdated. Analytical solution first helps you understand, in a very simplified scenario, some dominating effects in a very complicated problem. So one example I asked you last time was, suppose there is some void remaining in an engine, you've cast it, and now it heats up. Is it possible that it causes let's say, some significant damage to the engine material surrounding it? You will analyze that problem. So it's a simplification, but it will help you sort of analyze a quite complicated problem in a very simple setting. That's one. Two, if you want to do a numerical solution, sometimes it turns out the features of the solution are so tough to capture numerically that if you do some analytical analysis of the problem in a very simplified setting and try to insert some features of the problem into your numerical solution, and that's called enrichment, that is the terminology that one uses in numerics, you enrich your numerical solution with an analytical solution, and thereby make the cost of solving the numerical problem much, much lower. So these are significant things. So for instance, there are problems where the stress variations are extremely rapid, like at the tip of a crack. If you want to resolve that variation very accurately versus you try to do an analytical solution, enrich your numerical solution with the analytical solution at a crack tip, you can speed up your computation with 100 to 1,000 times. That's almost 2 to 3 orders of magnitude. So these are significant. These you do because you know how the analytical features of the problem are, and you understand, you are able to articulate those features, you are able to represent and solve for those features, and then you can insert them into your numerical model. So all of this stuff that we're doing, we're trying to develop these tools with which we can gain insight into complicated problems by doing certain simplifications, okay? So now that those remarks are away, let's go back to the essence, and we're going to solve. Now, the solution will look remarkably similar to what we've already done. So let's proceed. We have the displacement field. So the next step in our solution diagram is always the strain, which starts with the displacement gradient. Okay, so I'm, as usual, writing the non-zero components. That's the non-zero displacement of the non-zero components of the displacement gradient in a cylindrical coordinate system. So the last one is 0. So in our case, it's equal to u prime, u over r, and 0. And because it's diagonal, again, it's equal to the strain. Now, I mentioned at the beginning something about plane strain. So in this problem, what we have is that anything that has to do with epsilon z, right? Epsilon zr, z theta, zz, and rz, theta z, they are the same. They are 0, okay? This is plane strain. Right? It could be that anything that has to do with r or anything that has to do with theta is 0. Then we would also have plane strain. But this is a plane strain case that we are now encountering. And next time, we're going to look at a plane stress case. Let's look at the volumetric strain. That is some of the diagonals as usual. So it is epsilon rr plus epsilon theta theta plus epsilon zz, which is u prime plus u over r. And we can then move on to the stress, which is lambda epsilon v plus 2 mu epsilon. And so the stress is equal to lambda times that plus 2 mu. So lambda plus 2 mu u prime plus lambda u over r. And the second one is lambda plus 2 mu u over r plus lambda u prime. And the third one is simply lambda plus, or actually lambda times u prime plus u over r. That's the stress. Okay, so then comes equilibrium, which says that divergence of stress, because body force is 0, acceleration is 0, we have divergence of stress equals 0, and there is a component of the divergence vector only in the radial direction. So in cylindrical coordinates, that reads as follows. The other components are 0, so that has to be 0. The last two are identically satisfied, and the first one we need to enforce. Okay. So the only non-trivial equation eventually is the first one, which says derivative of sigma rr with respect to r, right? Sigma rr with respect to r. So lambda plus 2 mu so I'm writing the first component, lambda plus 2 mu u double prime plus lambda u prime over r minus lambda u over r squared, and then plus r sigma rr minus theta theta. So when I do rr minus theta theta, lambda u prime terms will cancel, lambda u over r terms cancel, so I only have 2 mu multiplying u prime minus u over r. So I'll write that 2 mu over here, u prime minus u over r is what I have left. And now, as usual, I will collect equal terms, terms that multiply equal terms. So lambda plus 2 mu multiplies u double prime, and then lambda plus 2 mu, again, multiplies u prime over r, and minus lambda plus 2 mu multiplies u over r squared, and that should be equal to 0. Okay, so as usual, we can get rid of the material parameters and then multiply through r squared, u double prime plus r u prime. Right, so we have this equation minus u is equal to 0. That's what we're trying to solve for. Now, in the tension and, in fact, torsion of the cylinder, and there we mentioned, so these are types of equations that pop up due to the symmetry of the problem that has often nothing to do with the problem itself. So again, we end up with actually exactly the same differential equation as we had in torsion and tension of a cylinder, and so we have solved for it. So now we know u is equal to, actually let me directly write it, C1 times R plus C2 over R. Now in those first two problems, just like in some sense to the spherical case, in the first two cases, in the tension and torsion of a cylinder, the second solution, of course, we omitted because R could go to 0, and that was not permissible, right? It was not permitted. And in the sphere problem, we obtained a solution that looked like C1R plus C2 over R squared. And there, R did not go to 0, so it was permitted. Likewise here, R does not go to 0 because the middle of the cylinder is just hollow, right? R starts from A. So again, this is not omitted. So R is A to B. So this solution here is permitted. So I will make use of it. And indeed, I have eventually two constants and I have two boundary conditions. I will be able to solve for those constants anyway. All right. So let's solve for them. Okay, so for that, we need to calculate sigma RR. Sigma RR is now unfortunately down there, but it's lambda plus 2 mu u prime plus lambda u over r. The solution is fairly simple. So lambda plus 2 mu u prime, which is C1 minus C2 over r squared, plus lambda u over r, plus lambda C1 plus C2 over r squared. So that's what sigma RR looks like. And if I collect terms that multiply C1 and C2, I have 2 lambda plus mu multiplying C1. And then I have minus 2 mu over r squared multiplying C2. Okay. And now this is supposed to be equal to, at r equals a, for instance, it's supposed to be equal to minus PA, because that is my boundary condition, the pressure on the inside. And minus PA, r is equal to a, so I can plug in r is equals a in that equation. So lambda plus 2 mu C1 minus 2 mu over a squared C2. And likewise, at r equals b, it should be equal to minus PB. So the second equation is that, okay, which together deliver what C1 and C2 are. So C1 is, let me write down the result, 2 lambda plus mu. So the constants look remarkably simple, of course, because it's a qualitatively similar problem to the sphere with a pressure case. And in that case, we had the second solution was of the form 1 over r squared. Eventually, that came or resulted in a 1 over r cubed dependence for the stress. So instead of r squared, we have an r cube. And instead of square terms, there we had cube terms. But apart from that, actually, these constants, even their forms, are almost the same, almost. And that's C2. Okay, so finally, I can also write down the stresses so we can discuss them a little bit. When I plug in the C1 and C2 values into our sigma RR, the material constants will disappear. So I have A squared PA minus B squared PB. B squared minus A squared, and minus A squared B squared over R squared. Okay, so sigma RR, I've done that very quickly because it's written on the board. The remaining two are not any harder. Let me write down the results again. So sigma RR, the radial stress, the tangential stress sigma theta theta, and of course, there is also a sigma ZZ. Right? Notice that epsilon ZZ is 0 because there is no displacement in our idealization in the Z direction, but no strain doesn't mean no stress, as we very well know by this time. So sigma ZZ is lambda over lambda plus mu. I'm evaluating this directly from that expression, right? This is sigma ZZ. I'm plugging the solution in there. I'm just writing whatever the result is. Better pause for a second. Okay. Okay, so significant variation in the tangential stress, significant variation in the radial stress. If it is really thick-walled, these terms will be of comparable magnitude. You cannot omit the radial one. You cannot omit the variation in the tangential one. Now, there is also an axial one. And we notice that the axial one has no dependence on R, right? There's an R there, there's an R there, there is no R there. It's a constant, okay? And why is the constant? So based on the sphere solution, I understand that, okay, I can relate to the nature of the solution, and that one as well. How about that one? Can I argue why it's a constant?
I separated the long one because we omitted the end effects.
We did?
That's why the R dependence is no longer there for the Z direction.
Yes, right, so based on the nature of the solution, perhaps I would suspect that it should be a constant, but can you give another argument that is perhaps based on our 231, 232 courses? Does it elongate? Do I allow it to elongate? I just omitted it, right? It does not elongate. To the contrary, it cannot elongate. And that's a starting point. But it wants to elongate, exactly. So if it were allowed, so suppose I had a strange, okay, I will slide this back down again. So suppose I put these two supports on rollers. Okay, that's like a very strange type of support. So in other words, right, I have magnet supports, right, which means it can pull on the cylinder. Now here, depending on the values of PA, PB, A, and B, I don't know whether this is tensile or compression. But let us suppose that it's under tension, okay? So the magnet supports originally can pull on this thing, but now they are on rollers, which means that as this thing tries to contract, for instance, they can just move and release that stress, okay? So the boundary condition for such a modified problem would be that not that displacement in the Z direction is 0, it would be something else, perhaps a linear variation, but that the axial stress is 0, right? When I say UZ is 0, I say that the axial strain is 0. That's sort of a condition I'm imposing from the outset. But in this case, it can contract. So what happens is there is the pressure, it expands in the radial direction, and it tries to contract. Why is it trying to contract? as it tries to expand in the radial direction, could it be possible that it tries to get longer? Is it possible? I pull on something. I pull on a rod. Does it get thinner or thicker? Exactly. It depends on the. So it depends. So can it get when I apply the pressure? Can it get longer? Yes, it might, depending on eventually whatever the Poisson ratio is. So whatever feature I'm observing here, it has to do with the Poisson effect, right? That's the simple answer I'm looking for. So all it's trying to do is trying to expand in the radial direction, and there are the end supports that constrict that contraction or expansion. So this sigma ZZ is nothing but a simple Poisson effect. So it's got nothing to do with the radial position. It's just in the Z direction a sort of a constant constraint. It's a constant stress. So I should somehow from this be able to see the Poisson ratio. So this is, as I mentioned before, sometimes with these constants you don't see it. But let me remind you once again that this constant you can easily see here, right? If I sum sigma RR with sigma theta theta, these two terms cancel each other, minus plus. I get 2 times that. So this is nothing but sigma RR plus sigma theta theta divided by 2, okay? So in other words, this thing here is equal to, let's not make everything red, it looks very aggressive. So that's equal to 2 lambda over lambda plus mu and sigma RR plus sigma theta theta. And it turns out that there are tables that you can look up for such constants. This is exactly equal to nu. Okay? And that's the Poisson ratio. So in other words, I have sigma ZZ equals nu sigma RR plus sigma theta theta. And here I see the Poisson effect. So now, having written that actually, right, so I'm just trying to always make the link to what we could easily do in 231 or 232 with this course. So this complicated solution, of course, we could not have done with our previous knowledge. We have to solve these differential equations. But in the end, remember the stress-strain relationship, but not writing stress in terms of strain, but writing strain in terms of stress. And in particular, if I write epsilon ZZ, UZ is 0, so epsilon ZZ is also equal to 0. That's equal to 1 over Young's modulus, the stress in the corresponding direction, sigma CZ, minus the Poisson effect, right? RR plus theta theta. Okay? So, since that's equal to 0, from this I obtain sigma ZZ equals nu sigma RR plus theta theta, which is exactly what I have got here as well. Okay? So it is no surprise that this should be the case. Okay. So the last thing I would like to do is consider one special case. So for the sphere, we considered several. But this one, in this problem, we'll consider only one. Which is the case where the outer pressure is 0, the inner pressure, let's call it P. So it's internally pressurized. And then you can simplify your solution. Sigma RR is, okay, I'm not making any assumptions. I'm just on the thickness or something at this stage. I'm just saying that the outer pressure is 0 so that the functions simplify a little bit. Okay, so now I will invoke the thin wall limit, just so we make sure that our solution is consistent with what we knew. And like last time, what we do is we define the wall thickness, T equals B minus A. And now we say that T over, let's say, A is much, much less than 1, which essentially means that A is approximately equal to B. And in the radial dependence to 0th order, you can say that whenever you see an R, you plug in an A. So this is a 0th order approximation in terms of the ratio T over A. So as I said last time, we could perhaps expand our solution in this parameter T over A and get various orders of approximation. But for T over A going to really 0, that's the approximation we can make. Now with that, so all I have to do is to make the approximation. Whenever I see a B, it's an A, R is an A. So this ratio is to first order. Let me write, approximately is equal to 0. So which means, in practice, that it can be omitted. Now that can be omitted, but on the other hand, if you look at that one, A squared 1, so it's essentially 2, right? So here we have B minus A, which is, sorry, B squared minus A squared, B minus A, B plus A, that's equal to T, that's equal to 2A. So that will be in the thin wall limits, approximately 2TA. So here we have 2TA cancels with one of the A's and a P. So this is approximately PA over T. There's a 2 there which cancels with that 2. Okay. And sigma ZZ on the other hand, let me squeeze it in there. So it is actually, I know, it is nu sigma theta theta plus sigma RR. So it should be nu times that. But if I plug in immediately here as well, I'll get the same result. This is 2TA, cancels with the 2. So you will again get nu times P times A cancels with that A over T. Okay. So it's still, of course, equal to sigma theta theta plus RR times nu, but RR is negligible. So it is, in this case, nu times sigma theta theta. Okay. Right, so that is our thin wall limit. And PA over T is, of course, an equation that we remember. So, do you have questions? So we could possibly, as you can imagine, go on forever considering different types of problems along the same lines with different degrees of symmetry. I can enrich these problems in innumerable ways, and we can continue forever like this. But I want to, at some point, stop displacement-based solutions, because I think we all understand how this machinery works. Except I'd like to consider one more case, which I'm going to consider last time. It contains some assumptions that we have not sort of considered before. It's going to be eventually a plane stress problem. And implicitly, it will involve some sort of acceleration. Okay, not a body force, but an acceleration. And it is essentially a disk that spins very rapidly. That's also a very classical problem. That will be the last displacement-based solution that we will look at. And then we're going to go to the other view of the solution approach, which is a stress-based solution. Okay? And then variants of these problems that we're considering, you're going to consider in the homeworks as well, and the midterm. Okay? So that's where we stand, right? So just to summarize, we started with the math part, and then strain compatibility, stress equilibrium. Those were the basics. And now we are looking at displacement-based problems, and then we look at stress-based problems, and we are pretty much done with the course. Okay. All right. So I'll see you next Tuesday.